So first of all, any questions on the data, the tabular data packet? Okay, we are going to hand that in tomorrow. And if you're not going to be here tomorrow, you got to make sure you get it to me before tomorrow. Okay, so okay, or by the start of class tomorrow. Okay, anybody have any questions on any of those? Tabular data packet. Anybody have any questions? Yes.
We did 5C.
5C. Okay. So we got a table here that is velocity. It says it's a differentiable function. So differentiable is always nice. When you're differentiable, that just means that's a good thing. Smooth, right? So smooth, not going to have any breaks or just nice, and things are happening like we think they might. Nothing weird going on. Okay. Now, it means smooth. So this doesn't mean it's going all the way from 0 to 9. It could go to 15 and then back to 9. That could happen, but it'll do it in a smooth fashion is what that means. So car B travels along the same road with this acceleration. So this data here is for car A. So car B travels along a road with this acceleration, feet per second squared at time t equals 3. The velocity is 11. Which car is traveling faster at time 7? Okay, so in other words, they want to know the velocity of A. So this would be the velocity of car A at 7. Well, we get that from the data, right, from the table. And what is that? What's that say? 61 feet per second. Okay. And so the question is, what's the velocity of B at 7? Well, we have an acceleration equation. So what do we do to get the velocity? We would do the antiderivative. So that would be t squared plus 2t plus c. Okay? How do we find the c? We've got our initial condition here. At 3, the velocity is 11. So we put an 11 there. We put a 3 there. So 11 equals 9 plus 6 plus c. So c would equal -4. So our velocity of B would be t squared plus 2t plus -4 or -4. And now we plug in a 7. 49 plus 14 minus 4 would be, what, 59 feet per second. Which car is traveling faster? Car A. Explain your answer. I would say your work really would be your explanation right there. Okay? So having to do it, you often, if you haven't kind of figured some of this out, and that's one of the things we'll be working on as we go into fourth term. We'll not only be learning and adding some new things, but the pace of adding new things slows down. Once we get past spring break, quite honestly, we're going to run through chapter 6. As a matter of fact, we're going to run through chapter 6 here before spring break. So we'll finish with a quiz on this stuff next Friday, okay? And we'll finish up chapter 6. We'll hand in this Niobrara graphing project on Thursday, and we will wrap up. But we'll wrap up chapter 6 with a quiz on Friday. And then when we come back from spring break, we're looking at, like I said, going into chapter 7, adding some new things, but it becomes, the pace of that slows down, and we focus more or as much on review and cleaning up, kind of like what we talked about yesterday in the video. If you were gone and haven't got a chance to watch that video, it's a pretty important video from the standpoint of big picture, how we use the integral. The different ways already we've learned about using the integral. To do some things, and it's really powerful, and it's pretty easy, really, quite honestly, when you get the idea of what the integral can do to solve these problems. It's really pretty easy, especially when you can just type it in your calculator and get the answer once you set it up. Okay, so we'll be cleaning up and looking at all the stuff we've learned and its uses and different ways to do it. Some of the technicalities that we may have skipped over on some things, we'll be throwing that in as well. Okay. Anything else in the packet? Any other ones you struggled with? They're very similar. As you went through each problem, you probably saw some of the same kinds of things over and over again. And again, the other reason I think this packet, I like to do this right now, this time, and again, we'll have to come back to it, but as we start reviewing and we get into the practice test and the old free response, almost every year, at least one of the free response questions has a table as a function, and it asks you that. And these are the types of questions you're going to have to do on there. So I want you to really feel comfortable when you see a table of data that you can do these things, these different things we've learned. Okay, we've been doing tables all along, but you know, it's just good to really look at it. Okay, what else? Anything? Okay, well, let's go ahead and put that aside and get your notes out. And a few people have turned it in already. So if you today, when we have work time later, you want to turn in that packet, you can. Okay, so let's take a look at this problem right here. This is another problem that was on the AP test in 2016, but not the AP test packet that I gave you guys yesterday that we were going over. Oh, by the way, those of you that were gone didn't get that, right? You probably heard that in the video.
Yeah.
If you watched the video. Yeah. What did I do with those? Okay, so who needs one of these 2016? Okay, so we will be working this out. We will be finishing this, as we go through the spring. So when you go on the video, one of the things you get with videos, we work some of these problems together. We kind of went through the ones that involve integrals. So as you go through the video, the ones we were working out are the ones on here. Okay? Or they were in this packet. Okay, so let's look at this problem here. So we were just talking about doing integrals with a table, and the only way to really do an integral with a table is to do a Riemann sum, right? You left rectangles or trapezoids or something like that. So that's what I really wanted you to practice on this packet for sure. And so of course we've done areas if we have graphs, especially if there's some geometry. We've done areas if it's an equation. That's easy. That's antiderivative, right? And we've talked about approximations too. But what we haven't done is if the functions are piecewise like this. So what we have is this one graph when x is less than or equal to 1, and then we have this other graph when x is greater than 1. So what do you suppose you would do to do the integral from 0 to 2? This is not in that packet, I'm sorry. So what I was saying, what reminded me about that packet, is this is from the international exam in 2016. It wasn't on the one in the U.S. But I've seen this problem before, or similar problem. So here you have a piecewise function, and you're supposed to do the integral from 0 to 2. What first thoughts? What do you suppose you'll do? Okay, now I agree. I think when I'm confronted with a piecewise function, I think one of the things that is good to do right away is at the break point, let's see what's happening there. Now it turns out it doesn't matter in this problem. But Cody said something important. He said plug a 1 in and see if it's continuous. That's a question we often get in these problems, isn't it? Is it continuous? Well, does the one take off at the same place the other one leaves off? So you put a 1 in here, you get 10 minus 2 is 8, 8 minus 1 is 7. You put a 1 in here, e to the 0 is 1, times 4 plus 3 is 7. Okay, so that just means that where the one graph ends, the other one will take off from the same place, and that's good. But it doesn't actually matter in this problem. If this one stopped at 1 and then this one took off like this, it actually wouldn't matter. But it doesn't. They are connected, so that's okay. But what do you suppose? So now let's go on to the integral part. What do you suppose you're going to do? Okay. Yeah, you're going to do the integral from 0 to 1 of 10 minus 2x minus x squared. So you go and write that down. And then you're going to do plus the integral from 1 to 2 of 3 plus 4e to the x minus 1. Oops, there's a 4 in there. It's really as simple as that. And you know what? It wouldn't even matter if they didn't connect. You would still be looking for that area right there. You'd still be looking for that area right there. Even though there's a hole there, it doesn't matter. It's okay.
This is for Bearcat time.
Okay. Thank you.
It's the leaky
All right. Geez, those are a little late. I think some of my Bearcat time kids went down today. All right. So anyway, just crazy how some people. All right. So anyway, here we go. So this was on the no calculator, as a matter of fact. 10x minus x squared minus 1/3 x cubed, right? I mean, just a little practice, antiderivatives, that kind of thing. How about this one? What's the antiderivative of this thing? Antiderivative of 3 would be 3x. What about that e to the x minus 1? Is that going to do anything? That's just a shift to the right. If there was a 2 in front of that x, like a 2x minus 1, we'd kick out a 1/2, right? But x minus 1, that's not going to cause any problems. So that's just 4e to the x minus 1, right? That's that. Yeah, that shift to the right, that kind of thing, that's no big deal inside there. So just normal antiderivative. And then that's going to go from 1 to 2. Okay, so we put a 1 in here, we get 10 minus 1 is 9, minus 1/3, that'd be 8 2/3. And then put a 0, well, they're all x's, you put a 0, that's going to be 0. Okay, so that's pretty easy. We put a 2 in here, 3 times 2 is 6. Put a 2 in here, we're going to get 2 minus 1 is 1, e to the first, that's going to be 4e to the first, 4e. And then minus, then we better put parentheses here, because I'm going to get some here. Put a 1, so that'd be 3. Plus, and then 1 minus 1 is 0, e to the 0 is 1, 1 times 4 is 4, 3 plus 4, so that'd be 7. So 6 minus 7 is negative 1, right? Am I doing that right? 6 minus 7 is negative 1, and then plus this 8 2/3, so that'd be what, 7 2/3? Plus 4e, yeah. There you go. So that was a free response question, so that's probably worth 2 or 3 points, probably for sure, probably 1 a point each for your antiderivatives, and then add them up, so that could have been a 3 or 4 point problem, actually, maybe. Okay, but yeah, it's just like you think it would be. Yeah, it's that simple. So you got piecewise function, splits it at 1, so you do the integral from 0 to 1, and then you do the integral from 1 to 2. So pretty simple if you run into something like that. All right. Okay. Let's go ahead and start. I don't know how you title out your notes. Oh wait, one other thing. One other thing here. Sorry, this was left over from yesterday too. I thought we'd done enough yesterday, and I did want to add one more thing. So let's talk about it right now. So again, some of this stuff's just not in the book, but it's things you have to know for the AP test, and it's one of the reasons I like having this AP test or final kind of to point towards, because it really is good at putting everything together. And that is one of the advantages of having 3 terms, is kind of that time to put things together, right, that we've been learning. And so I want to talk about average. So for a long time in this class, I've been saying that average, when you hear the word average, you think what? Well, especially average rate of change. Slope between 2 points. For a long time, I said, when you hear the word average, we're not going to add up and divide by how many we have. That's not the average we're talking about. Average rate of change is what we heard a lot. Average rate of change means slope between 2 points. Average rate of change means slope between 2 points. So, but now we've learned a new average. What's the new average we've learned with integrals? The formula we just talked about yesterday. Average what? Average value of a function, right? The one that's the integral over b minus a. So now we've got 2 things that have the word average in them. But so now we need to be a little more specific about how we talk about them. So let's do that. So one example is if you ask the average rate of change of f. If you ask for the average rate of change of f, you're saying do the slope between 2 points on f. So it'd be f of b minus f of a over b minus a. So let's do an example of velocity. So let's say I ask for the average rate of change of velocity. Now, what is another name for the rate of change of velocity? Acceleration, right? But average rate of change of velocity would mean do the slope between 2 points on velocity. So v of 10 minus b of 8 over 10 minus 8. Look at the units. You'd have centimeters per second up here. Divided by seconds, you'd have centimeters per second squared, which is acceleration. Okay, so that was slope between 2 points, average rate of change. Okay, now we bring in this new fella here, this thing called average value of a function. So let's say we had another problem where I said, find the average value of the acceleration function. Find the average value of the acceleration function. Okay? Well, we've already said that if you find the average value of f, you do integral of f divided by b minus a. So if I want to do the average value of acceleration, I do the integral of acceleration divided by 10 minus a, or 8, right? That's our formula. But notice I'm saying the average value of acceleration. So I do the integral of acceleration. So up above, I had asked for the average rate of change of velocity. So we did b of 10 minus b of 8 over 10 minus 8. That was the average rate of change, slope between 2 points. Average value of acceleration, saying use the average value formula on the acceleration function. Integral of acceleration over this. Now, what's the antiderivative of acceleration? Velocity. So you do the antiderivative, which is velocity, and you do fundamental theorem part 2. So you do v, so you plug in a 10, you plug in an 8. Look what you get. Same thing. So let's compare those two. So what we're saying is the average rate of change of velocity is the same thing as the average value of acceleration. There are two different formulas, but they end up being the same thing. So what's the big deal about that? Well, it's not a big, there's nothing a big deal about it, other than there is that connection. But most problems, you'll be able to tell the difference between which one you're looking at by the wording. If it says find the average rate of change of something, then you do the slope between 2 points. If it says find the average rate of change of something, you do the slope between 2 points. If it says find the average value of something, then you do the integral of that something over b minus a, right? That's easy. But what if the question was this? Because this is what you're going to see. Find the average acceleration. What if it doesn't say rate of change, or it doesn't say average value? It just says find the average acceleration. Which one would you do? It's a trick question. They're the same. It doesn't matter which one you do, but it matters which function you use. So somebody in the other class actually kind of had the right answer when they said, it depends what they give you, right? If they say average acceleration, if they say find the average acceleration, and they gave you a velocity function, then what would you do? You would do the topping. Because you would be thinking to yourself, here's the thought process. You'd say, they want the average acceleration. This is velocity. Well, acceleration is the rate of change of velocity. So what they're asking you for is the average rate of change. That's slope between 2 points. Now, the other thing you can always do is say, if they're asking for average acceleration, you know your units need to come out to be acceleration. So you need velocity divided by seconds, okay? But if they give you an acceleration function, and they ask you for average acceleration, now they're asking you for the average value of that function. If they're saying find the average acceleration and they give you the acceleration function, they want the average value of that function. So now you're using the average value formula. So you do the average, the integral of acceleration divided by this, and you would get that. Okay? So that may happen with just the word average. It does say rate of change, it doesn't say value. Well, it depends. Depends what they give you, which one you're looking at. So that's just something, it's a neat connection between those two things. Again, we see the connection with integral and slope, okay? But also, how would you handle that if you saw that in problems? Okay, all right, so let's turn our attention to chapter 6 here. Let's run through this real quick. Well, not real quick, but let's get through what we're going to be doing today. You are going to be doing some writing out again, kind of like when we're doing the sigmas, but we're not going to be as picky about it this time, and we're going to have some rules to it. I told you that chapter 6, we're going to dive a little deeper into this. Now, don't write this down. This is what we already had written down. I'm going to give you something else, another way to write these here, okay? But if you want to start a new page in your notes, whatever. But this is chapter 6, okay? So in chapter 6, it's pretty short, but we're going to dig into the details of left, right, midpoint trapezoid a little bit and approximations, okay? And we're going to talk about the error. We're going to talk about the how they're off. You know, why are they approximations? Why aren't they exact? What makes them be off? When will they be more off than other times? That kind of stuff. That's what we're going to be getting into. Okay, so here's what we're going to do. We're going to rewrite these a little bit. Okay, I wanted you to write these out, height, width, height, width, height, width. And I was real picky about how you wrote it because we were doing sickness. So we need to see the pattern. Well, we're not doing sickness now. So the patterns aren't as big a deal. So if we're just going to write these out to care about the final answer, that's what we care about now. Before we didn't care about the final answer, we were trying to write them as signals. Okay, we want to see the patterns. Now we care about what's the actual final answer. That's what we're after. Okay, so there'd be some smarter ways to write this. For example, if we have equal widths, we're going to pull out the width. We're going to factor out the delta x. Okay, so if we take a left, so this I would like you to write down. So if we take a left rectangle, we're going to factor out the delta x, except how do we find delta x? It's b minus a divided by n, right? So let's, instead of factoring out delta x, let's factor out b minus a over n. Let's actually write that out there. Okay, so you know, remember the first thing we always did was find the width? Well, now we don't have to do that. We just plug it right into there, and that'll be the width right on the outside. So we're taking out the width, and if you're doing a left, what are you going to do? You're going to do the first y value, then the next y value, then the next y value. You're going to go all the way to the next to last y value, right? Because you don't want to use the far right edge if you're doing lefts. Okay? So that's how you'll see me write out left rectangle approximations from now on. I don't care. You can still do it the way we were doing it. You can do height times width, height times width, height times width. That's fine. Okay? All right. And then what's a right look like? What's different? You're going to start with x1 this time, and you'll go all the way to x sub n. You won't use the first y value. So think about if you had a table of data, right? If you're doing right, you would not take the first one, but you take the next one, the next one, the next one. Now you got to be careful with the table of data. Table of data might not have equal widths. This doesn't work if they're not equal widths. Remember we did the one yesterday where we took the first y value, we're doing lefts, we took the first y value times 1, the next y value times 2, the next y value times 3, because the widths were different. You had a width of 1, then a width of 2, then a width of 3. If that's the case, you have to write it all out. Okay, you don't have a choice. Okay, midpoint, same thing. We're going to take out the width. And then we'll have our first midpoint, our second midpoint, our third midpoint, right? All the way out to there. Okay? So this is, again, this is how you'll see me in the future. This is how you see me write these out typically. Okay? Again, it doesn't matter if you're doing an L4 and you have to write out 4 rectangles. You want to do height times width, you know, for all 4 of them. That's fine. That still works. Okay, not a problem. All right, now the trapezoid one's a little interesting. The trapezoid one, we not only can take out a delta x, but what else? We can take out the 1/2. Now the delta x is b minus a over n, and if you take out a 1/2 also, basically what you have is a 2n on the bottom. You basically have b minus a over 2n. And then what are you going to have left? You're going to have 1 of the first one. You're going to have 2 of the next one. You're going to have 2 of the next one. You're going to have 2 of all of them except the first and the last. So your trapezoid is going to look like this. So your trapezoid is going to be b minus a over 2n. So we bring out the delta x, we bring out the 1/2, and then you're going to have the first left endpoint, then you're going to have 2 of the next, 2 of the next, 2 of the next, 2 of the next, all the way until the last one. Now, something important to understand. This one is going to have n items in it. This one's going to have n items in it. This one's going to have n items in it. Because if you're doing an L4, an R4, or an M4, you have, these are the heights, right? So this is your 4 left heights, your 4 right heights, or your 4 midpoint heights. So if you're doing an L4, R4, or M4, you're going to have 4 items inside those parentheses, 4 heights. But how many are you going to have here? No, you're going to have 1 more. Because here you're using the left one and you're using the far right one. So you're going to have 1 more. You're going to have n plus 1 items. So if you're doing a T4, you should have 5 of these in here. Okay? If you're doing a T8, you should have 9 of those in there. Okay, 1 more. Now, this first homework assignment today is all supposed to be really no calculator. Well, you can use your calculator to do the adding, but you have to write it out. You have to write out the sum. Now, our rule's going to be, if you have less than 10 subdivisions, we're going to write it out. If we get more than 10, that's going to be our next homework assignment, actually on Monday. then I'm going to give you a program for your calculators that can do it. So if I ask you to do an M20, you're going to type it into your calculator. Or if you have to do an L50, right, you're just going to type it in the calculator and let it calculate. But if it's less than 10, you got to write it out by hand. That's the rule. So we get to the homework, that'll be, or the test, the quiz, that'll be, okay?
And less or less than?
Single digits. So less than 10. Okay? Less than 10. All right, and here's a new one. This is called Simpson's rule. So you see the S here. Simpson's rule, S sub n. Okay? Now, Simpson's rule looks a lot like trapezoid rule, but it's got a few differences. It's b minus a over 3n. We'll find out here in a minute why it's a 3. And there's, just like trapezoid has 2, 2, 2, 2 in it, trapezoid uses one of the first, the far left edge, then it uses 4 of the next, 2 of the next, 4 of the next, 2 of the next, and the 4, 2, 4 pattern continues all the way till the end where you just use 1. And there's always a 4 right before the 1 at the end, just like there's a 4 right here. Because of that, Simpson's rule always has to have an even number of subdivisions. So again, there's always going to be n plus 1 here, but that always has to be odd. There always has to be an odd number in here for this 4, 2, 4 pattern to work. Now that's not true in trapezoid. You can do a T7, and there would be 8 items in here. Okay? But for Simpson, we have to have an odd number of items in there for the 4, 2, 4 pattern to work. So Simpson's rule will always be an even number of subdivisions. Okay, now you're going to see why in a minute. Okay, it has to do with midpoints and trapezoids and so forth, and why it has to be even. So I will never ask you, I'll never try to trick you. I'll never ask you for an S7. Okay, you'll do an S4 or an S6 or an S8 or an S20, but you'll never be asked to do an odd one. Okay, so it has to be an even number of subdivisions because of this 4, 2, 4 pattern. So it's very closely related. Now, it's much more accurate. Why do we need Simpson's rule? Here's why. Because if you want to get real accurate, you can do a million left rectangles. It's going to be accurate. Probably it's going to take a long time. Even for a calculator, it's going to take a long time. Okay? Trapezoids and midpoints are more accurate, but it's still going to take them a long time. So Simpson's rule is even more accurate than those. Okay? So you need a lot less subdivisions so it can calculate it much faster. So your calculator uses, I'm not sure what your calculator uses when it approximates, to be honest with you. I think it's a version of, it's an even better version of the Simpson's rule, I believe. Okay? So it's able to do the, remember when we typed in that integral that didn't have an antiderivative, gave us a decimal, how's it know? How's it know that's what we're investigating here in Chapter 6? How's it know that that's accurate to 10 decimal places if it doesn't know the right answer? How's it know? That's what we're going to investigate in Chapter 6. Okay? But if it was using left rectangles or trapezoids, it would take too long. It'd be too slow. Okay? All right. So now, we're going to look a little deeper here at trapezoid and Simpsons. We have some shortcuts for these of where they actually come from. Okay, well, trapezoid, we know where it comes from. It's because of trapezoids. Okay? All right. Don't write all this down. Just write this part down right here. Just write that part down. Now, you can write it off to the side of your trapezoid one if you want. This is a shortcut for doing trapezoids. Because trapezoids are nothing more than averages of the left and right. Now, I think we've already mentioned that earlier. But think about it. If you have a picture here, and you have a left rectangle, and you have a right rectangle, the trapezoid is just the average of those two. Okay, the trapezoid is just the average of those two. All right, now we can show it, and that's what I'm going to show you, but you don't have to write this down. Okay, so when would you ever use this? Okay, when would you ever use this? Well, if I give you a problem and just say, do a T4, I think it's faster to write out the first one we wrote down, the long one. B minus A over 2n, do your left, do 2 of your next, 2 of your next, 2 of your next, and then your last. That's probably faster. But a lot of the homework today, they're going to ask you for an L4, R4, M4, T4, S4. Well, it'll be S8, but we'll see that in a minute. Well, if you've already done L4 and R4, then by all means do this for T4. Just take L4 and R4 and average.
So just show that
Okay.
on 3, right?
You don't have to rewrite it. So you can just show that, and you can just put your L4 plus your R4 divided by 2. Just write that down, and then your answer, and then you got it. Okay? So this is an optional one you can use for trapezoid. It's best used if you've already calculated L and R, then just average them and you got T. Okay? Now, let me show you why that is. Okay? So here's L, and here's R. So if I add these together, okay? If I add these together, I would have my B minus, they both have a B minus A over N out in front, so that'll be out in front. And then I'd have one of these, I'd have two of these, I'd have two of these, I'd have two of these, and then finally at the end I'd have one of those. So I only have one of those, and I have two of everything else. Well, that would look like that. And then we got to divide by 2, right? So we divide everything by 2, and sure enough, we end up with our trapezoid. B minus A over 2N, and then our 2 pattern shows up. So it's easy to see that a left plus a right divided by 2 is the same as a trapezoid. Okay? All right, now, we have a shortcut for Simpson's rule. So write that down. Okay, now, you don't have to write that x-axis that I wrote over there. Don't worry about that. But I'm going to show you that here in a second. Simpson's rule, now notice it says S of 2N. Now, I didn't say that on the other one, so that's important. So the long one we wrote out is S of N. So if it's S of 8, that's your N, is 8. Okay, so when it says B minus A over 3N, your N would be 8 in that formula. Okay, so S of N, that formula was this. But for this formula, it's S of 2N. Here's why. Because we want these to be half in here. We want these to be half. Okay, now remember I said that Simpson's is always even, right? So that's why the 2N is in there in this one. So what that means is if you're doing an S6, so you probably should write this down too. So if you're doing an S6, that means you do 2 M3s plus a T3, and you divide by 3. So if you're doing an S6 and you're using this shortcut, you do 2 M3s times a T3. So this would only be useful if you've already done M3 and done T3. Then you can do this to get S6. So that's why your homework, I don't think, should fool you. It might. Most of the homework's going to do this. It'll ask you for an L4, an R4, an M4, a T4, and then an S8. And since you already have the M4 and the T4, then you can plug it into that to get the S8. Make sense? Now, if the problem asks you for an L4, R4, M4, T4, and S4, what do you need to do the S4? You need M2 and T2. Then it's up to you to decide. Would it be faster to do an M2 and a T2 and then do the S4? Or would I be better off just doing the longer version of the S4 we had earlier? That's up to you, right? But if it says do an S8 and you already have M4 and T4, then you just plug into this. Okay? Now, what is this? This is a weighted average. This is called a weighted average. You know, you ever had a teacher that said, okay, we're going to take your first test and your second test, but we're going to count the second test twice. Any teacher ever done that? They're going to count this test twice. Okay? So you take your first test, you take 2 of your second test, you add them together, you divide by 3. That's called a weighted average. A weighted average. So this is a weighted average. We're going to take 2 of the midpoints, 1 of the trapezoids, and divide by 3. Now, why a weighted average? Well, here's why. We're going to learn here in a little while that whenever a midpoint approximation is done, it's always a little more, roughly twice as accurate as a trapezoid. So a midpoint is actually better than a trapezoid approximation, closer. And not only that, but if a midpoint is over the actual answer, the trapezoid is under every time, and vice versa. But we're gonna see why here in a little bit. Let me say that again. If a midpoint is over, a trapezoid is going to be under. So averaging them is a good thing. That should get us closer to the right answer. Not only that, but the midpoint is even closer. It's off by less, almost half. So what's that mean? Well, if a midpoint is over and it's off by 0.2, and the trapezoid's under and it's off by 0.4, if we average them, we're going to be off still. But if we take 2 of the midpoint, so think about that. The midpoint was over by 0.2. If we take 2 of those, now we're over by what? 0.4. And the trapezoid's under by 0.4. Now we average them, we're right where we want to be, right? Now, it's not exactly half, or twice as accurate, but it's close. So that's why it makes sense to do 2 of the midpoint ones and 1 of the trapezoid ones, okay, to average. All right, so that's our little bit of a formula. Now, I'm going to go through, don't worry too much about this part, but I just want to show you that this is the same as this down here. I want you to see where the 4 and the 2 pattern comes from, okay? So, it comes from this. So, we're going to take our M3 and our T3. Okay, so, if we were just going to do our T3, this would be our T3 right here. It'd be these points right here. So, normally we would call that X0, X1, X2, X3. But we're going to need to do our midpoints too. So I need to have a name for our midpoint. So if I call them X0, X1, X2, X3, I don't leave any room for my midpoints. So I'm going to call them X2, X4, and X6. Then my midpoints will be right here. X1, X3, and X5. So I'll use those for my M3, and I'll use these for my T4, or T3. Okay? So here's my M3. Remember, it's B minus A over N. And then my first midpoint, X1, X3, X5. Those are my midpoints. Okay? My trapezoid, remember, is B minus A over 2N. N is 3 here, okay? And I use my first left, which is X0, then 2 of the next one, then 2 of the next one, 2 of the next one, right? So the big ones are my trapezoids. Remember, I'm only doing a T3, so that's 3 subdivisions right there. 1, 2, 3 subdivisions. And then I got my midpoints of each of the 3 subdivisions. So it's an M3 and a T3. Okay, now I'm going to add these together, okay? Now, I got to take 2 of my midpoints, right? So first I want to take 2 midpoints and then plus my trapezoid. So I got to take 2 of these. Well, if I multiply this by 2, that doesn't do me any good out here. I'm going to distribute it through. I'm going to have a 2 and a 2 and a 2. So each of my midpoint ones, X1, X3, X5, are going to have a 2 on them. Okay, everybody see why? Because we're going to do 2 M3s. Okay, so I'm going to multiply through by 2. Okay, now I want to add these together. Well, what's the problem right here with these fractions for adding? What's the problem here? What do you got to have to add fractions? Don't have a common denominator, right? Don't have a common denominator. So, when I go to add these up here, I need a common denominator. So I'm going to multiply by 2, right? Well, I'll leave this 2 down here because I need it for my common denominator. What am I going to do with this 2 up here? Distribute it through. So what's going to happen? 4, 4, and 4. See why we get a 4 on the midpoint ones? We get a 4 on the X1, the X3, and the X5. We got a 2 there because we had to multiply by 2 for the 2M. And then we got another 2 because we had to get a common denominator. Okay, now I can add those up. So when I add those up, I get B minus A over 6, right? Because 2 times 3 is 6. I got 1 of these. I got 4 of those. I got 2 of those. I got 4 of those, 2 of those, 4 of those, and then 1 of those. 4, 2, 4, 2, 4. Okay, now what I haven't done yet is divide by 3. I haven't divided by 3 yet. Okay, so now I got to divide by 3. Remember, this is my n because I'm doing an S6, right? I'm doing an S6, so that is my n. So I divide by 3, and now I got my 3n. So now we can see where the 3n came from. Back here, we can see where the 3 came from because that weighted average divided by 3. Okay, and there it is, B minus A over 3n, 4, 2, 4 pattern. All right, so I just want you to see where that came from. So, 2 ways you can do an S6. You can either write it out like this, or you can do the M3 and the T3 add. All right, let's do a problem and see what that looks like. Okay, so this will be some of what your homework's going to look like. We're going to write some of it out, and we're going to get your calculators out. We're going to just calculate one. I'm going to show you some little tricks you can do to speed things up on your calculator. Okay? And then we're going to talk about over and under approximations real quick. And then I'll let you work. And at the end of the period, we'll talk about the graphing project a little bit. All right, so here's an integral. Notice it says I equals. So in this chapter 6, they often will call the actual area I for integral. Now, we know this is an easy one. We can do the antiderivative of that. 1/3 x cubed, 0 to 2. So that'd be 8/3 minus 0, which is 8/3, which probably nice to do decimals, right? Probably nice to do decimals on our area. It just sounds better. 2.667 sounds better as an area than 8/3. Okay. even though it's rounded. But it'll help us to see how far off we are in our approximations. Now, you might say, why would we even do approximations if we already know the exact answer? That's a great question, but we're just trying to learn the process here, so when we get to the ones where we don't know what I is, we don't know the exact answer, right, then we can still do this same process. All right, so in your homework, it's going to be like this. They're going to say do an L3, R3, M3, T3, S6. Well, right away, that's single digits, so that's a hint. We got to do this by hand. We got to write it out. That's automatic, right? Single digits, we're writing it out by hand. Okay, now, if you want to just do height, width, height, width, height, width, I don't care. You can do that, but I'm not. I'm going to use the new ones, the new versions we've been using. So this would be B minus A over N, right? Now, I probably need an x-axis over here, 0 to 2, just like we did last week. We're going to divide this into 3 subintervals. So what's this first one going to be here? What's my width? We already did the width. It's right over here. The width is 2/3. So this is going to be 2/3. This is going to be 4/3. Now, I don't care how you write them now. We're not going to write the 2 as 6/3. We're not finding patterns anymore here. So we don't care about that. So whatever's easiest for you to type in your calculator is what you want to go with. Now, I wouldn't do 0.666 because that's rounded, so I would write it 2/3. Okay? So what's my first left right here? So I'm going to put f of 0 plus f of 2/3 plus f of 4/3, and then we stop, right? We don't go all the way to the right edge, right? We don't go all the way to the right edge. Okay? Because it's left. So notice we don't have to worry about the width. We factored that out. So the width is outside of it. So all we need is our first left and our next and our next, whatever. Okay, now remember, we said if you're doing an L3, you should have 3 items in here. 1, 2, 3. That's what we have, 3 heights. Now, here's where the calculator is going to help you. Here's what I would do if I was you. I would write it out in F notation first, because that's just easier, depending whatever the function is. Now I would go to your calculator. So everybody do this. Just go to your calculator, go to your menu, go into your calculator screen, go to your menu, go to define. So under menu, very first option, go to define. Let's define f of x to be x squared. Now, I don't care if you do it this way. If you want to type in 0 squared, you want to type in 2/3 squared, you want to type in 4/3 squared, you want to do all that, that's fine. Maybe you can do it faster. I'm just saying this might not be a bad way to do it. So define f of x equals x squared. So define f of x equals x squared. Now what you can type in then, once you do that, once you hit enter, now you can just type this in. Now this is 2/3, so I would just type that in. So I would just 2 minus 0 do in your head, right? So 2/3 parentheses f of 0 plus f of 2/3 plus f of 4/3 close parentheses, hit enter. Okay? And now not only that, but I think you can go up and grab that the next time when you want to do your rights or whatever, and then you can just change some of the numbers that you need to. Okay, yeah, f of 2/3 plus f of 4/3. So once you type it one time, yeah. Then once you type it one time, I think you can go up and grab it, and you can just change, edit a few of the things. What do you get for an answer? Let's get a decimal on that. 40/27 is 481. So obviously it's an under approximation, isn't it? Okay. Now let's write out our R3. Our R3 would be 2 minus 0 over 3. And then parentheses, and then what's our first right? F of 2/3 plus f of 4/3 plus f of 2. And see, I don't even care that you write that 6/3. There's no reason. You don't need to see the pattern. So just write it like that. But again, this will have to be on your paper. This written out part has to be there when we do our homework, when we do our quiz. If it's single digits, the rule is we write it out. Now, once we've written it out, you can use your calculator from there. Once you've written it out, and if you want to write out f of 2/3 times 2/3, f of 4/3 times 2/3, f of 2 times 2/3, if you want to write out height times width, height times width, height times width, I don't care. That's fine too. Okay? All right. I don't know why you would, but anyway. What do you get on this one? 4.148. All right, okay? All right, and then I don't even care about this next one, what the answer is. Let's just get it written out. Okay, I'm going to move along here and leave you some time. What's our first midpoint? Okay, the midpoints now we got to calculate. So that's going to be 1/3. What's this one? 3/3 would be 1. And then 5/3, right? And again, I wouldn't write it 3/3, I'd write it 1, because that'll be easier to type the calculator. So this is going to be f of 1/3, and then our next midpoint is f of 1, and our next midpoint is f of 5/3. And then whatever that equals, I don't care. I'll give you that answer here in a minute. I'll give you those answers here in a minute. So don't worry about writing those down. Okay, now, what are you going to do to get T3? You're going to do, and I'm okay if you just write this. If you just write L3 plus R3 divided by 2, and then I'll give you that answer here in a minute. Don't worry about it. Okay? That's all you got to do. Now, probably what you want to do is go up on your calculator and grab your unrounded values that you have from earlier. Don't round them. Don't take these two numbers, but go up and get your unrounded values, add them together, divide by 2. Okay? All right, and that's going to be your T3. And then what are you going to do for an S6? 2 M3s plus T3 divided by 3. And then you're going to do that right there. Okay, because you already got your M3. Remember, to do an S6, you need 2 M3s, a T3, and then you divide by 3. So we're just going to do that. That would make the most sense, instead of writing it out the long way. Now, I'm going to show you a screen here where I think I wrote it out the long way, but I wouldn't do that on this problem. I would do those formulas. Okay? All right. So, here's what I had for the answer. So I had the midpoint was 2.593, if you want to write that down. 2.815 is what I had for the trapezoid. And look at that, the Simpsons was actually exact. Was the exact answer. Okay? Now, it's not a coincidence. There's a reason it was the exact answer on this one. It's not always going to be the exact answer, but on this one it was. Okay, now, I want you to notice something here. Here's going to be the last thing we're going to talk about. Notice that the lefts were under. Here's x squared. It's increasing, right? So isn't it obvious lefts, the red ones are going to be under, right? The rights are over. But look at midpoints and trapezoids. The midpoint's under and the trapezoid's over. And that's not a coincidence. Midpoint trapezoid are like partners. Left and right are like partners. If the left is over, the right's going to be under every time. If the midpoint's over, the trapezoid's going to be under every time. Okay? So they're opposite each other. They're partners, but they're opposite each other. Okay? The midpoint's a little more accurate. It's a little closer to the exact answer if you check it. Right? If you take this and subtract that, it's only about 0.08 away. This one's about 1.5 away, 1.6, about half, right? That's what we talked about. Okay? Now, or 0.18, okay? Or 0.16, I mean. So anyway, let's discuss this over-under thing just a little bit. I think we kind of know common sense-wise, at least the first part of it. Oh, I'm sorry, one last notation thing, and then we'll talk about over-under. One last notation thing. You're going to see this a lot in this chapter. Okay? You're going to see this right here in this chapter, I minus L. What was I? The exact area. Okay, I is the exact area, the interval. What's L? Well, right, it's a left approximation. It's an approximate area. So, what do you get when you subtract them? What would you call that? The error. It's not percent, but it's the amount of error. Okay, so I would put these terms in there. So, I is the exact area. L or R or T or M, whatever was in there, those are approximate areas. So if we subtract them, we get the amount of error, how much we're off. Now we put the bars around it just to make it positive. If it was negative, that means it's either over or under, whatever, right? If the approximation is less, then that's going to be positive. If the approximation is over, then that's going to be negative. We don't care about that part of it. We just want to know how much are we off. So that's what this, so when you see this in your head, you just think, okay, that's the amount of error. That's the difference between the exact area and our approximation. Okay, so that's just some notation just to make sure you understand. Okay, let's talk about this real quick. This will be the last thing, then I'll let you work for a little bit, and then you can, and I'll talk about the graphing assignment at the end of the period. So what is going to make a left rectangle be under, or excuse me, over the graph? If the graph is going down. If the graph is decreasing, then a left is going to be over. What's going to make a left be under? If the graph's increasing, a left is clearly under. Okay? Pretty easy. What about a right? It's going to be opposite. If the graph is increasing, a right is going to be over. If the graph is decreasing, a right's going to be under. Okay, so this isn't like something you memorize. This is just something you probably could draw out and just think about, right? So a graph's going down, a left is going to be under, but a right will be over. So they're always going to be opposite. So even if the graph goes up, then down, then up, then down, the left and rights will work out. If one of them is under, the other's going to be over every single time. Okay, now here's what makes a trapezoid be over. No. Here's a trapezoid right here. That trapezoid is over approximating that area. Why? Why is it above? Why is that straight line here above the curve? Because the curve is concave up. Because the curve curves below that straight line. And to do that, it's got to be concave up. Now, and so you said decreasing, right? It doesn't matter. Increasing or decreasing, it doesn't matter. A trapezoid is going to be over if this graph is concave up. And then likewise, what if it's concave down? Here's your trapezoid. Your trapezoid is going to be under. So a trapezoid is going to be under when the graph is concave down. You don't have to memorize it. You just draw yourself a little picture. Draw yourself a little picture and you can see what makes a trapezoid be over or under. It's the curve. Boy, if we only had some sort of thing that would measure when a graph is increasing or decreasing. Or when a graph is concave up or concave down. Okay, there's more to come on that later. All right, what about a midpoint? What's a midpoint? Why is a midpoint a partner with trapezoid? Why is a midpoint going to be the opposite of this? Okay, it seems weird because here's a graph and here's a midpoint rectangle right here. Right? Here's a midpoint rectangle right here. Some of it's over, some of it's under. How do we tell if it's over or under? How do we know? Well, I want you to imagine this. Imagine I took a tangent line right here. Right? That's not very straight, but you get the idea. Okay? Now, imagine I drew this trapezoid in blue right here. Everybody see the blue trapezoid? Everybody see the blue trapezoid there? Yes, Squint? See the blue trapezoid? See how the top of it is like pivoted around that midpoint? See how it's pivoted right around that midpoint? Okay? Now, what can you tell me about this little triangle here? Oops. What can you tell me about this little triangle here and this little triangle here? Aren't those equal areas? Aren't those going to be congruent triangles? Look at your old angle side. What do you got right here? You got right angles right there, right? What do you got right here? What kind of angles are those? Vertical angles, they're equal. What do you got right here? Oh, don't you know that's a midpoint? So isn't this side the same as this side? Angle, side, oh, I said angle, side. Angle, side, angle. These two triangles are congruent. So what happened was when we took our red midpoint rectangle and we chopped off this piece of area and added it over here, isn't this blue trapezoid the same area as the red rectangle? The blue triangle, you're not shaking your head, shake your head, yes, shake, there you go. This blue pivoted trapezoid, let's call it a pivoted trapezoid, this blue pivoted trapezoid is the same area as that red rectangle was. And is that blue pivoted trapezoid over or under? Is that blue trapezoid over or under the area under the curve? It's over. It's over. It's on top of the curve. Here's the area. the area is underneath the red curve. That's the area of the red curve. The blue trapezoid is more. It's over top. Okay, so think about that. A tangent line, and so what we have, so here's what you can think of. A midpoint rectangle is really a pivoted trapezoid, and it's a tangent to the curve. So if the thing's concave down, the tangent's going to be above it. If it's concave up, where's the tangent? If it's concave up, the pivoted trapezoid is going to be here. It's going to be below. And where's your regular trapezoid? Your regular trapezoid is there. It's above. That's why midpoint trapezoid are always going to be opposite. Okay? So a midpoint is going to be an over when it's concave down. It's going to be an under when it's concave up. And again, all you have to do is you just draw it, and you remember, okay, a midpoint is the pivoted trapezoid. A midpoint is the pivoted trapezoid. Okay? So it's going to be under when it's concave up, which is the opposite of a regular trapezoid, which is over when it's concave up. Okay? So you're going to have some questions about over and under approximation. They're going to ask why. Well, you're going to say because it's concave up. All right. So 6.1 homework. So you can work on that here for about 15 minutes or so. And then I'm going to interrupt and talk to you about the graphing assignment just a little bit. Okay? We're going to talk a lot more about tomorrow and show you some things there. But yes.